uncover the mysteries, because the mysteries are like, okay, where does this where the stuff come from? I don't know. Okay, so you have the initial composition. And the second one says that if you know the temperature, and here's the temperature, you can see where you are at. Like, this is the composition and this is the temperature. Map that tells you, based on the composition and the temperature, what phases are present. Any questions? Yes? Easy? Okay. The second rule, if we know temperature and the initial composition, we can determine the composition of each phase. Now this part is a little tricky. Okay? And let me explain. If we are in a single phase region, here, or here, like this is solid, this is liquid. Whatever this composition is in terms of the weight percent nickel, that is the composition. But if we are in the two-phase region, where is the two-phase region? It's right here. It's the white color, and no color. The composition of each phase is determined by the tie line. I can assure you that I know material science better than her, but that's okay. I think I do, unless we do the matrix trick, and I give you the flash card, or the flash graph. Okay, we covered this before. Can anybody answer me the question of how you determine the phase composition based on the tie line? Looking at this. Anybody? It's okay. Okay, what is a liquidus line? What does it mean? What's the meaning of a liquidus line? And what's the meaning of the solidus line? How far are you guys in the help session? Like, what are you covering now? Last time, what did you cover? Do you go to the help session? Chapter 6. Okay. Well, I showed you this stuff before. It's not rocket science. You should be able to answer by looking at the picture. What do we have above the liquidus line? Why is it called liquidus line? Liquid. Okay, good. What do we have below the solidus line? Solid. What do we have in between? We have both. We have two phases, liquid and the solid. Okay. How can we determine the composition of each phase? We draw a horizontal line, which is called a tie line. And where this line intersects with the solidus line, that's going to be the composition of the solid phase. And where it intersects with the liquidus line, that will be composition of the liquid phase. Okay? So take a look at this. We are started with 35% nickel. And in liquid, it's still 35% nickel. But at T sub B, we have, which is 1250 degrees, we have the composition of the liquid as 32% nickel, and the composition of the solid is 43% nickel. And it kind of like makes sense if you think about it in terms of the ice and water. Whenever you have ice forming, we need to form those nuclei, and those nuclei start to grow. And to get the party started, you need to have somebody dancing on the floor. Have you been to a party and there's music playing and nobody's dancing and you're like intimidated to go because you're like thinking like, no. So sometimes for like a party, they hire people to go and dance on the floor, professional dancers or professional entertainers, just to get the party started. So here, to get the party started of solidification, we need to get, I'm not that entertaining. See, when people walk out on the show, I don't like it. I don't like it. It hurts my feelings. Like, what the heck am I doing here? They have more important things to do. Okay. Do you have any questions of how to determine the concentration of the liquid and the alpha phase based on the second rule? Because there'll be problems that you would have to solve, and we might as well sort it out now. If you don't get it, this is the time to ask questions. Okay. I asked you a question. What is the percentage? What is the meaning of a percentage here? Can you explain to me what this percents mean? Yes? Not yet. We didn't get to that. It's coming. But the reason I'm asking you this question is so that we differentiate two types of percents. Exactly from what you said. And what is this? We're talking about composition of each individual phase. Okay? So this is the weight percent of nickel in the liquid phase and the weight percent of nickel in the solid phase. And once the solid phase is forming, it needs to have a little bit more of nickel for solidification. And then there's going to be more atoms diffusing from the liquid to the solid, forming the nucleus. Yes? Rule number 3. That's exactly what you were talking about. If we know the temperature and the initial concentration, we can determine the fraction of each phase. Okay, now this is important before we dive into the actual numbers. Those fractions of the liquid and the solid, how many percent would that be? Altogether. 100%. Okay? Thank you. So you start with the alloy of certain percentage of nickel, and all you do is you just heat it up. That's all we do. We don't do anything else. We just heat it up. This is going to save you time on the exam and doing the problems, because once you know the fraction of one phase, you can find the other one. How? By subtracting what you found from 1. Okay? So please remember that. If you go back here, then this is a different percentage. It does not have to add to 100 or whatever. Do you get that? Yes, sir.
The composition only adds 400 when we add all 3 C's.
3 C's. What are 3 C's?
The C, that's the L, and the C.
No, nothing adds to 100 here. This is the composition of nickel in liquid and composition of nickel in solid. This does not add up to 100%. That's what I'm trying to explain to you now. And I'm trying very hard. I'm trying to do a much better job than ever before. Seriously. Because you can read the book, you can read the slides. Who's going to explain to you what the heck this actually means? How many of you are reading the book? Okay, so how do you study? You're expected to do some problems, and you don't even understand what it is. So this is what I'm seeing a lot lately with graduate students. is they're doing stuff because they're told to do. Okay, yeah, my mother told me to go get some bread. And I did get some bread when I was like 6 years old or 7 or 8. And I brought the change and I was a good boy. So whenever you do something, when you get a job, you should understand why you're doing it. What's the objective? Okay, and that's what I'm trying to, discuss here. So here, the composition of individual phase could be anything. It doesn't have to add to 100%. But when we're talking about the weight fractions, this stuff has to add to 100%. So let's consider this 35% alloy. We see that at the point A when we have liquid, and the weight fraction of the liquid phase is 100% or 1, and the weight fraction of the alpha phase is 0. There is no solid. Yes, sir?
So I just wrote the composition again. The composition of the CL is for 2 liquids, the C alpha is for solid. What's the C0?
C0 is your alloy that you start with. That's what they gave you. That's your alloy. You made it, or you bought it. C0 is the initial concentration. You take this much nickel and you take this much copper and you put it in a melting pot and you melt it and stir it however you made this alloy. Yes? Okay. The magic of material science comes right here. What happens in between? And the composition is the most important part, like how it's going to change, because this is what's going to control the microstructure. Okay, at point D, what do we have? We have solid, no liquid. So the weight fraction, or the fraction of the liquid phase is equal to 0, and the solid phase is equal to 1. Now, the trick here is in between, because we're going to use the lever rule and the tie line, because here both alpha phase and liquid phase are present. And the tie rule is similar to this, a teeter-totter. Have you ever played a teeter-totter when you were a kid? Some kids were heavier than others. So this is how it works. You have mass here and you have mass here, and it's balanced, so it's horizontal. Okay? Do you understand the lever rule? Teeter-totter? Okay, that's where it comes from. So for this to be horizontal, it needs to be balanced. Okay, and then we can write that the mass fraction of the alpha phase times this lever S is equal to the mass fraction of the liquid phase times R. Where does this come from? If you know. I know we have like 3 majors here. Mechanical engineering students are supposed, I'm expecting you to answer. And civil too. Where does this equation come from? Moment. Okay? And that is called a moment diagram. Have you taken a class called statics from Nora? Who took that class? Did he do a good job teaching you? Industrials, I'm not asking, because you haven't taken statics, right? You're taking it now. Okay, you're going to get your ass whipped, but that's okay. Okay, equilibrium of forces in the moment. This is the balance of the moment. If you take this point and you balance the moments, so this is the force in terms of the mass times 11, right? And so is here. And for this to be an equilibrium, this is the balance equation. The moment here is equal to the moment on the right. Okay, and we're using it here, but I'm not telling you where it's coming from. It's coming from Nora. Everything comes from Nora in the engineering, from statics. What's it, statics is a prereq for industrial?
Yeah.
For which course?
It's just required.
The same. And here's the equation, how you would calculate the weight fraction of the liquid phase, which is equal to ml divided by ml plus m alpha, or it's equal to S divided by R plus S. So it's equal to this divided by the whole thing. And I don't know, I don't care how you remember it. Like if you say it's the opposite lever, because it is S divided by R plus S. But legally, it's equal to the C alpha, this, minus C0, which is that, and that's the length of S right here, divided by the whole thing, which is C alpha minus CL, or the whole lever. And you're taking a fraction. And that's how you determine, based on rule number 3, the weight fraction. And the weight fraction is how much liquid you have, how much solid you have. Capiche? Okay. Let's have a look at what happens with the microstructure. And it's shown schematically. Well, it's very important that we just go through that. At point A, we have liquid. The concentration is 35% nickel, weight percent nickel in this phase. We hit the point B, and the precipitation of nickel starts over here at 46%. So those little nuclei, those little tiny guys, have 46% nickel. And the liquid phase is at 35%. Doesn't change. And then there's more nickel atoms that in the liquid diffuse to those nuclei. And then at the point C, the concentration of nickel dropped down to 43%. Concentration of liquid also dropped down to 32%. And this nuclei became bigger. The liquid phase has 32% nickel. The alpha phase, the solid phase, has 43% nickel. You see, they don't add up to 100%. They should not. It is the composition of each phase. How much nickel is in each phase? By the way, what's the rest? What are we looking at here? What's the alloy? Copper nickel. So, if there's 32% nickel, how much copper is there? $68. You get that? Okay. Then we continue to drop temperature down to this point D. Okay. This guy's grew, and the composition of the solid phase is 36%, and the composition of the liquid phase is 24%. So you see that there's more nickel that goes into the solid, into this nuclei, and it's a diffusion process. And in the liquid, it's easy for the atoms to diffuse, much easier than it is in the solid. Okay, then we go down to point E, and all this nuclei are less, and they form a grain boundary, and the composition is 35% nickel. We started with 35% nickel, we ended up with 35% nickel. But in the meantime, we went through the process that's called nucleation and growth. And as a result, there's something that's called pouring. Because this little guy in the beginning has 46% nickel. By the time it's all done and solidified, it's 35% nickel. So there's a concentration gradient, which is not a good thing. Anytime there's a concentration gradient, what does that mean? What is it causing? Concentration gradient? You just inflated your tire, but you forgot to put a nipple, and you disconnect your pump, what's happening? It deflates. So pressure is like a concentration gradient. So we don't want concentration gradients. We don't like concentration gradients. What do? We want equilibrium structure. So we homogenize this. We raise the temperature to allow the diffusion to happen so that there's continuous concentration without the coring. What's the motto of material science? To control the process, to control the structure, to control the properties. Can you guys remember that? I was talking to NSF program director yesterday in polymers division who sent my proposal back. He said, oh, we look at our polymers program from this perspective, to control the process, to control the structure, to control the properties. How, Mr. Walensky, did you propose to characterize the properties of these polymers? Did you suggest some X-ray diffraction using synchrotron sources? You know. Okay, please take a look. Tensile strength versus composition of nickel, and elongation to failure versus composition of nickel. From 0 to 100%. You see? So, how do you do control? You pick up the composition you like, and if you want the alloy to have the maximum tensile strength of 400 and blah 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 megapascals, you would pick up a composition of 60%. You see that? But the reason it's doing it is because of all this. That controls this, to control the process, to control the structure, to control the property. Okay, eutectic. Man, they underemphasize eutectic in overall. And look at this phase diagram. This is called eutectic phase diagram. And it has this kind of like butterfly. And this is copper, silver phase diagram. What's the melting temperature of silver? 100% silver. Look, how do you find it from this phase diagram? Okay, well this is 100% silver. Let's go up. Ba 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 ta 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 ta. Alpha plus beta. Here's beta. Beta is what? Solid or liquid? Liquid. Yes? I can bullshit you here all day long. Is beta a liquid? No. There's only one phase that's called liquid, that's called L. Alpha and beta phase are solid phases. Alpha phase would have more copper, and the beta phase would have more silver. Yes? Okay. So we go from here, and this is pure beta, which means that there's limited solubility, and this means that the beta phase is all silver. There's no copper here. And then at this point it melts because it starts to form a liquid. What's the temperature? Roughly. Right here. What's the temperature? It's close to 1,000 degrees. That's the melting temperature of silver. Okay, let's look at the copper. We start here, we go up. Is alpha a liquid phase? No, it's a solid phase. And then what's the melting temperature of copper? It's right here. You see that? Like what, 1100-ish or so? And I have a question for you. If we take an alloy with a composition of C sub E, eutectic, what is the melting temperature of this alloy? (779 degrees centigrade). I will show you another one. And the reason you have your cell phone in your hands and the reason you're carrying that laptop is because of this phase diagram. Okay, this is tin lead, which is solder that's used to take all of those components that you have, all those chips on the printer circuit board, which is made out of plastic. And let's have a look. So this is lead tin, and this is percent tin. So here it's 100% lead, and here's 100% tin. What is the melting temperature of lead? 300 and something degrees. What's the melting temperature of tin? 200 something degrees. What's the melting temperature of the eutectic of 62% tin, and the rest is 38% lead? You see it here? It's 183 degrees. So here's the material science alchemistry. You take component 1, which is tin. You take component 2, which is lead, and you melt them together. And that alloy melts at a lower temperature than each component separately. And of course, I went through training and I went through graduate school and all that good stuff. You know how I learned, like really truly learned what this physically means? I started a job with a Motorola. They hired me as an SCM engineer because you need to look at the microscope. And we were supporting production. So on a Friday night evening, when you want to go out or just get out of there, Friday evening, you know, production never stops. They have people working 24/7, different shifts, all that. And once the line is down, they need to find out why, because there are thousands and hundreds of thousands and maybe even millions of dollars of lost revenue because the product is not being pumped out and shipped so that you can get your cell phone and your printer and whatever else. And this guy brings me a wafer that has gold on silicon. And they said we annealed it at 400 degrees C, and I stick it in the microscope and I see liquid drops. So silicon and copper form a eutectic, and they annealed it, and there was something about the process which is irrelevant what was wrong with the process. The bottom line is that gold deposited on silicon melted the silicon, and they were like raindrops on your car windshield. That's what I saw. And I explained to the engineer what the heck eutectic means and why it happened. I had the knowledge to do that, luckily enough. I did not become a hero, but I didn't go out that night on Friday. Okay, do you understand this? Did I do a good job explaining what eutectic means? You take two components, and you melt them together, and as an alloy, it melts at a lower temperature. Not all of the systems are like that. Not everybody, just some. Okay. So we can write the eutectic reaction, which is also called, all of those reactions are invariant reactions. What's an invariant reaction? You see those lines, pointers, arrows? They go both ways. So this reaction happens upon heating and upon cooling. You see here, it doesn't go to 0, it goes to 8%. So the reaction is that the liquid of 71.9% silver, upon cooling, is decomposed into the alpha phase that has 8% silver, and the beta phase that has 91.2% silver. And if we look at it more carefully, this is forming what's called a lamella structure. And this is how it works for the lead and tin or we have the streaks. See that? And one is primarily tin and the other one is primarily lead. Okay? I'm running a little ahead so I can try to explain to you before we get into the details, because the details kill the good science and explanation. Yes? All right. So binary eutectic system. Binary means that there are two components. Eutectic means that there's a specific composition with minimum melting temperature. And I tried to do a very good job explaining to you. And this is what you need to be aware of. So going back to your cell phone, how do they make the motherboard for your device? There's solder paste, and using some sort of a printer, they take the printer circuit board, or they take a mask, is another way. Any of you had your cell phone repaired at a shop? No? The way they do it is that they have a mask. And a mask is a metal that has holes in it, like this. And those holes are very tiny. And they put it on top of your device, on top of the motherboard. And they take a paste, and they, for those civil engineers, kind of like when you take the, what do you call it? The stuff that bonds bricks together. Cement and cement mix, because cement with sand and water, that's the cement mix, right? And that stuff is it's viscous. It can go through holes. So you take a knife and you go through this mask, and then you take this mask off, and then you have one part of the board and you have another part of the board, and you put them together and you heat them up. And you only need to heat them up to 183 degrees centigrade. A little bit more, maybe under 200. Because if you heat this thing above 200 degrees C, you are going to destroy your components, your chips and whatever, capacitors, resistors. They cannot survive this high temperature. There has been a big push to have lead-free solder. Have you heard about that, lead-free solder? Because what do you do with your cell phone once you're done with it? Toss it. And where does it end up? Landfill. And which country? Who knows? Lead is toxic. Actually, there's a shitload of materials that are toxic in your cell phone. And can you imagine how many people live in China? Is it 1 billion people already? What about India? What do they do with their cell phones? What do they do with all of those incandescent bulbs and lights and old air conditioners and all that junk? You know? Living in the United States is easy because there's always somebody who'd want to buy your used car, and they drive. Have you been to, I haven't been to Cuba, but you can imagine that Cuba is full of antique cars back from the 60s that were left by the Americans. And they still run there because, you know, they cannot buy anything new. Okay. Let's get into the details. The eutectic reaction at 183 degrees C, we draw the tie line, and we see that the composition of the alpha phase, this was asking for 40%, and for weight 40% tin and 60% lead at 150 degrees C. So we're here. We are asked to determine what phases are present. And the answer is alpha plus beta, 2 phases. The composition of the alpha phase is 11%. The composition of the beta phase is 99% tin. So alpha phase is primarily lead and beta phase is primarily tin. And then the other question is to find what is the ratio. Like how much alpha phase is there, how much beta phase is there. It's a different question. So these are different percentages that I've been talking about, right? R divided by R plus S is going to be the amount of the alpha phase. This is equal to the C beta minus C0 divided by C beta minus C alpha. This is the confusing part. It's always been confusing to me. So as long as you call it R and S, you're okay. Because it's S divided by R sub S and R divided by R plus S for the alpha and the beta phase. But we here determined that the composition of the alpha phase is 67% tin, and we can use the lever rule as well to determine the 33%. This could be a way for you to verify that you've done your calculation right. But they need to add to 1. The next question, what about 220 degrees C? What phase is it present? Here, what phase is it present? Are we in Tampa or Gulfport? Where are we? Here. What are the 2 phases? Solid and the liquid. What's the solid phase? Because we have 2. We're in this region, so it's L plus alpha. They're going to be labeled for you. You know, city of Tampa, city of Gulfport. We have liquid and the alpha phase. What's the composition of the alpha phase? We draw the tie line. The composition of the alpha phase is 17% tin. The composition of the liquid phase is 46% tin. See that? We draw the tie line. What's the fraction of the alpha phase? Well, now we use the lever rule. CL minus C0 divided by CL minus C alpha. 46 minus 40 divided by 46 minus 17, or 21%. And the rest is the liquid of 79%. These are different percentages. This is our percentages in terms of the composition, and they are in weight percent. Here the percentages are just a fraction. Let's take a look at microstructure, how it develops. We start from the liquid, we drop down. The first phase is alpha phase. And it happens when the composition is less than 2% tin. So we take this composition here. And you cannot dissolve anything, and we're only going to have tin. So the minimum concentration you would start would be tin. You'd start at 2%. You cannot dissolve less than that because this is a single phase region. And it's going to have the composition of C0. Well, let's say we drop in a little more tin. Between 2% and 18.3, we're going to have alpha plus the beta phase range. So we're going to have alpha grains and beta particles. Those little tiny speckles. You see? This is the alpha phase, is shown here as blue. and then we're going to precipitate the beta phase, the pixie dust. And the beta phase is going to be primarily the why? Because 18.3% is the solubility limit of eutectic. You see 2% to 18.3%. Here we have alpha phase. We drop down the temperature, we get alpha plus the beta phase. The beta phase precipitates in solid state. There's no liquid involved. This is your it's called precipitation hardening. Because all of a sudden you have particles of the beta phase, and it has different composition, it has different structure. Okay, what if we are at the eutectic composition? That's when we're going to form lamella structure. And the one is going to have 18.3%, and the other one is going to have 97.8%. And it's going to look like this. That's what I was trying to show you. One is going to be lead rich, and the other one is going to be tin rich. So those atoms, they have a choice where to go, and that's why the lamella structure is formed like this for eutectic. Now what we can also do through the microstructure control, we can have primarily alpha and eutectic alpha and eutectic beta if we're close to this composition here, once we solidify it. And we can calculate how much of that. So you see, what matters is the composition of your alloy. And what you need to know is you need to have a phase diagram like this to do your microstructure control. There are two types of systems for eutectic: hypoeutectic and hypereutectic. So if you're on the left side, you hypoeutectic, and if you're on the right side of the eutectic, you are hyper. And the difference is this: the particles that are going to precipitate for hypo are going to be alpha. You see them here as black, and this is the eutectic composition. No precipitation of the secondary phase. And for hypereutectic, you have precipitation of the beta phase. And it looks different on the microstructure. You see it's gray and not black. And one is rich in lead and the other one is rich in tin. And it's around 62%. So by formulating this alloy, you can do a lot of cool stuff with your microstructure. Now, sometimes it's called an intermetallic compound. An intermetallic has the exact stoichiometry. Magnesium 2 lead. You see, it has to be at 80%. And they're shown on the phase diagram as a line, as a vertical line, at fixed value. Because you need to account for stoichiometry. This is a chemical compound. So whenever you see like a straight line, that means that there's an intermetallic. For a process, it's not good to have intermetallics because they make your stuff brittle. Okay, other reactions. We talked about eutectic, and it's when the liquid upon cooling goes to alpha and beta, or alpha and beta upon heating goes to liquid. There's another reaction called eutectoid, and the eutectoid reaction is happening in solid state. So we have one solid that's getting decomposed upon cooling into two different solids, or the two solids get composed into another one. And the difference is the N, tic versus oid. Eutectic, eutectoid. And another one is also interesting, it's called peritectic. Peritectic means that you have a solid that's reacting with the liquid to give you another solid. And we're going to talk about this iron-carbon diagram for steel and all that. That's this other reaction. Here is an example of peritectic transformation. We have gamma plus liquid, and upon cooling it's going to form the delta phase. This is copper zinc phase diagram. You see? And this is the famous iron-carbon phase diagram that which we're going to spend a lot of time on. There are two important reactions. There's eutectic reaction here, happens at 1148, and then there's a eutectoid reaction that happens at 727. So in eutectic reaction, we are forming gamma phase, the austenite phase gamma plus iron 3C. And for the further cooling at 727 degrees C, we have austenite decomposing into the alpha and the iron 3C phase. Just remember these two temperatures. 1150 and 730. These are the most important temperatures that we're going to be using for heat treatment of steel. This iron 3C is called cementite, and it's very hard. Alpha is called ferrite, and it is soft. So there are high eutectoid steels that are on the left side here. And here's the corresponding microstructure. Like below here. And there's high eutectoid steels in this region right here. And we're on the right side. So look at the percentage in terms of the carbon, from 0.76 to just over 2%. See, there are only two phase diagrams that they give you in the VMSE, lead tin. And this is interactive. So what you can do, look, you can take a composition here, you see, and I can drag it down so it's all liquid. Pa 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 da 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 da. Oh, 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 oh. You see? I'm causing in this region precipitation of the solid phase. You see? This circle's here. I can drop it down. This is actually very cool. Boom. Wow. Man, this is really old stuff. I mean, I had it on a floppy back in the day, but now they must have written some JavaScript for this. But this is how you learn, really. Oh, here you can do any composition. It's showing you how the rings coalesce. So you're dropping down the temperature from any composition. to control the process, to control the structure, to control the properties. Like this is going to determine the size of the grains, and the size of the grains determines the strength. Alloying elements can change the temperature of the eutectoid reaction. You can see alloying of steel with nickel or magnesium drops it down, chrome, tungsten, silicon, moly, titanium increase it. But for steel, what are the main ingredients of steel? Iron and carbon. Both are cheap. All of this stuff is expensive. This is the, what is this? Concentration of the eutectoid changes, so you can also change the concentration. It's all written here as the weight percent of those alloying elements. So you try to make stainless steel, you add chrome, nickel. Example problem. For 99.6 weight percent iron, 40% 0.4 weight, iron 0.4% steel at temperature just below the eutectoid. Determine the composition of cementite iron 3C and the ferrite alpha, and the amount of cementite in grams that forms 100 grams of steel. The amount of perlite and pro-eutectoid ferrite in 100 grams. So this is like a fancy way of asking you that percentage of each phase. Okay, the composition of the alpha phase here is 0.022% carbon. How do we determine this? Right here. The composition of the ferrite is 6.7%. You can see this phase diagram. Look at this phase diagram. It only goes to 6.7%. Because past that, it's going to be cast iron. Cast iron has a lot of carbon. For the steels, actually below 2%. So using the lever rule, we can try the weight fraction of the iron 3C. Okay? It's R divided by R sub S. And it's 0.057. So that means in 100 grams, we're only going to have 6 grams of cementite. Very small amount. The percentage of the C0, we start with 0.4 weight percent. That's given in the problem. The composition of the alpha phase is determined by the style line, is 0.022%. So we can figure out the weight fraction of perlite, and that is 0.5, meaning that we're going to have 50 grams. So half of that. Man, I spent the whole semester on this phase diagram. We're going to come back to it. All right, so we introduced phase diagrams. I hope I did a wonderful job teaching you Jiu-Jitsu. But it's not going to be enough. You'll have to read on it and do problems, because there's just not enough time to go over this. You have to do it in practice. And I can tell you the most important things, figuring out what are you being asked to do. All those percentages. What do they mean? The percentage composition of the phase is determined in weight percent. So it has a different percentage. WT. You see? This is in weight percent. The percentage of the liquid versus solid is in the actual percentages, not the weight percentage. Although we did convert it to weight, which has made it even more confusing for you, but that's okay. Right here, because they asked you about 100 grams. Phase diagrams, composition, microstructure, eutectic, eutectoid, peritectic. Okay. Now we will discuss phase transformations. And here you see iron and carbon. This is austenite. Upon eutectoid transformation, it transforms into iron 3C and ferrite, which is BCC. So we had austenite, which is FCC. Upon the eutectoid transformation. Eutectoid transformation is what? A solid plus a liquid forms another solid, right? Okay, eutectoid means in solid. So we had FCC, it forms to BCC. And how does it happen? All of the phase transformations happen by the process of nucleation and growth. Going back to your ice cubes that never froze for your party, so you asked whoever's coming to your party to bring ice, remember? Nuclei are small seeds that act as the places where the stuff starts to grow. There are two driving forces for this to happen, either supercooling or superheating. If you have small supercooling, you have slow nucleation rates, less nuclei in large grains. Large supercooling, rapid nucleation rates, many nuclei in small crystals. There is homogeneous nucleation and heterogeneous nucleation. But this is the most important graph. And maybe I'll have a chance to show you the video. This is Gibbs free energy. We have the surface energy term, and it's positive, this red line. It's equal to the 2 pi r squared gamma. 4 pi r squared gamma. Gamma is the surface tension. So surface tension is trying to collapse your nucleus. Surface tension is a driving force to make it the smallest. But as we are growing big, the internal energy starts to grow, and it has this blue curve right here. It is equal to 4/3 pi r cubed. What is the mathematical formula for 4/3 pi r cubed? This is the volume of a sphere. This is the surface of a sphere, 4 pi r squared. And this is the volume of a sphere. This is times gamma, which is the surface energy, and this is times gamma sub v, delta G sub v. And the total energy is this sum. So if we add this curve and this curve, we get this green curve, which is going to give us the radius of the nucleus. And how do we determine the maximum? We take a derivative, right? Because right here, the derivative is going to be 0. And that allows us to calculate the critical size of the nucleus. And if this nucleus is less than this value, then it's going to get redissolved. If it's higher, it's going to get growing. So with that, hopefully I will show you the video.
You want to see water freeze almost immediately? Well, here's what you're going to need. Some very pure water. Fiji water has been recommended to me by a friend. And obviously we're going to need a freezer, some way to cool it down. So I'm going to put this bottle of water in the freezer in the area normally occupied by the ice cube trays, because I think that might be the coldest part of my freezer. I've got 2 bottles just in case one doesn't work. And now we have to wait.
You know this guy?
There are lots and lots of videos showing this phenomenon on YouTube,
Now you know.
but very few that explain how it actually works. So I'd like to take a minute and do that. Water is normally a liquid at room temperature because the water molecules are all flowing past each other, tumbling around each other, and that allows the substance to flow. When something becomes solid, its molecules all more or less lock into place. They still vibrate, but they're not rolling over each other and moving past each other, so they can no longer flow. They're solid. Now what we're doing here is supercooling the water. So we're taking it below its temperature, below 0 degrees, where it should become ice. But it's very difficult for that water to make the transition without somewhere for that ice crystal to start growing. So what we need is some kind of nucleation event. If the water is not pure, the impurities in the water naturally act as sites where the crystal can start forming. That's why it's very important that we use very, very pure water. Another way we can cause this nucleation event is to bang the water bottle. Hopefully that will cause a few water molecules to line up in the right way, and that will seed the rest of the ice crystal. So let's give it a few hours, and we'll come back and try to nucleate this ice forming event. All right, it's taken a few days and multiple attempts, but I think this could finally be it. I might have finally created supercooled water. So let's find out. I'm going to take the water very carefully out of the freezer.
See, he moved it. It was in a different place. Oh, what?
And then you can see clearly that the water is still liquid. You can see this air bubble floating around. And now I'm going to bang it on the counter, and we will see if we can get an ice crystal to form. Whoa, look at that. You can see that ice crystal growing right down from the top to the bottom. So there you have it. I was finally able to demonstrate the supercooled water phenomenon. I cooled down the very pure water in my freezer for 2 or 3 hours, and then by
20 million
banging the water
views.
bottle on the counter, I started the formation of an ice crystal. It was
This is the guy who's like super famous back in the day when the virality on YouTube was not driven by artificial intelligence. You know, you would say, "Oh, have a look at this video, 20 million views, not too bad." But we're going to go over this next time. But the idea is that you have 2 competing events. One is the surface energy that collapses the nucleus, and another one is the internal energy. And they have the opposite signs. So we add these 2 equations together, 2 curves, and we get the master green line, which is Gibbs free energy. And based on that, we can calculate what is the minimum size of the nucleus that's required for this to happen. Okay? I'm planning to come to the help session tomorrow, just to check it out. Because there's a faculty meeting and I'm going to be here. I'll see you on Tuesday.